Welcome to the Explainer. Today, we are diving into one of the most fundamental tools in all of data science, linear regression. Now, I know, it sounds kind of complicated, right? But stick with me. It's really just about finding a straight line in your data that, believe it or not, can help predict the future. Let's break down how it all works. So let's kick things off with a big question. Can data really predict the future? I mean, can a bunch of numbers tell you what's going to happen next? Well, no, it's not a crystal ball, but what it is a super powerful technique for finding hidden patterns. And once you find those patterns, you can make some really smart forecasts. It's not magic, it's math, and we're about to see exactly how it's done. All right, so where do we even begin? How do we find one of these predictable relationships that's hiding in our data? You might be surprised, but it almost always starts with something really simple. Just looking at it, drawing a picture. Okay, let's make this real. Imagine you're running a business, right? You've got all this data on how much you spend on marketing each month and how many sales you made. Each one of these little dots you see here, that's a month. The million-dollar question is pretty obvious. Is there a connection? I mean, if we pump more money into marketing, do we actually sell more stuff? And this, right here, is where something called simple linear regression comes into play. It's basically a method for figuring out the relationship between two things. You've got one variable you can control, that's the independent one, like your marketing budget. And then you've got the one you're trying to predict, the dependent one, like sales. And the whole idea is to connect them using a single, simple, straight line. And voila, here's what we're trying to do. We take that cloud of data points and draw a line right through it. Suddenly, we have a model. It's simple, yeah? But it's also incredibly powerful. Because now, this line isn't just a summary of the past, it's our rule for the future. We can pick any marketing budget we want, find it on the bottom, go up to the line, and boom, get a pretty solid guess at what our sales are going to be. But wait a minute, you're probably thinking, you could draw a ton of different lines through that data, right? A million of them. So how in the world does a computer know which one is the perfect one, the absolute best fit? Well, the secret sauce is all about measuring the mistakes. Seriously. For every single one of our real data points, we can measure how far away it is from our prediction line. See those little vertical lines? That distance has a name. It's called a residual. And really, it's just a fancy word for the model's prediction error, or its mistake for that one point. So how do we get to that best line? The method is actually pretty slick. An algorithm basically tests out a potential line, and for that line, it measures all of those little errors, the residuals. Then it does something kind of nerdy. It squares each error. That just makes them all positive, so they don't cancel each other out. Then it adds them all up. The goal? Super simple. Find the one and only line where that grand total of mistakes is as tiny as it can possibly be. That line, that's our champion. That's the best fit line. Okay, so we've done it. We've found the line with the smallest possible error. But here's the catch. Just because it's the best line we could find, does that mean it's actually any good? I mean, is it a useful predictor? We need a way to grade our model to see how well it actually did. And for that, we have a fantastic little metric called R-squared. The easiest way to think about it is like a report card for your model. It gives you a score somewhere between 0 and 1, and that score tells you exactly how much of the change or the variance in your sales can be explained by your marketing budget. It's a grade. Let's actually see what these scores look like. Check out the top left. An R-squared of 1, that's a perfect score, an A++. Every single data point is sitting perfectly on our line. Our model explains 100% of what's going on. Now look at the top right, 0.70. That's still really strong. The data is packed in pretty tight around the line. That's a good model. But as you can see, when the data points start to scatter out, that R-squared score takes a nosedive. A score of 0.36? Not so great. And down there on the bottom right, 0.05? That's pretty bad. It's basically telling us that our marketing budget is a really weak predictor of sales. The connection just isn't there, and our straight line isn't helping us much at all. But let's be real. In the real world, something like sales is almost never caused by just one thing, right? Life's more complicated than that. So a lot of the time, trying to predict something with just a single factor, it's just not going to be enough to get a really good prediction. Here, check this out. If we build a model using only TV ad spending to predict sales, we get a pretty decent R-squared of about 0.82. Not bad at all. But watch what happens when we add in the data for radio ads. Whoa. The score jumps all the way up to 0.91. That's a massive improvement. It just goes to show you, sometimes adding more ingredients makes the recipe way better. And that leads us perfectly into something called, you guessed it, multiple linear regression. It's the exact same idea we've been talking about, but instead of using just one thing to predict our outcome, now we're using two or three, or hey, maybe even hundreds of different factors all at once. The result? A much more detailed and hopefully much more powerful prediction. Of course, adding more stuff isn't always a free lunch. It can bring new headaches. We have to worry about a trap called overfitting. That's where your model gets so complex it basically just memorizes your existing data, including all the random noise, instead of learning the actual pattern. We also have to be on the lookout for multi-collinearity. Sounds scary, but it just means our predictors are tangled up with each other. Like say you included both the temperature in Celsius and in Fahrenheit. They're telling you the same thing, and that can really confuse the model and mess up your results. Okay, and all of this brings us to what might be the single most important lesson in this entire explainer. And it's this. You can't just blindly trust the numbers. You just can't. The statistics your model spits out are not the whole story. You can have a model that looks absolutely perfect on paper. I mean, a fantastic R-squared score, great-looking stats, the whole shebang. And it can still be completely, totally, 100% wrong. And if you don't believe me, look at this. This is the absolute classic example of that danger. It's called Anscombe's quartet. Now, get this. All four of these charts, they all produce the exact same statistical summary. I'm talking the same average, the same variance, even the very same best fit line with the exact same R-squared score. It's wild. But just use your eyes. Look at them. Only one of them, the one in the top left, actually makes any sense for a straight line model. And that right there is why you must always, always look at your data. You have to plot it out first. A simple picture, a simple graph, it instantly shows you things that the raw numbers would totally hide. You can see a weird curve, you can spot a crazy outlier. Visualizing your data is your #1 defense against being fooled by the stats and jumping to the wrong conclusion. So in the end, what does this all mean? It means that tools like linear regression are incredibly powerful, for sure, but they are not a substitute for your brain, for human observation and critical thinking. Think of them as a fantastic starting point, but never, ever the final answer. The data gives you clues, but it's still up to us, to you, to look closely, to ask the right questions, and to figure out the real story the data is trying to tell.